Okay, we'll start. Yeah, welcome guys. Welcome to the annual work seminar. This seminar and some of the work that we did as part of the LUMOS project, and we'll focus more on the architecture parts. So the LUMOS essentially trying to build a platform so that people can train their own deep learning large models. But we'll cover some of that, but mostly we'll focus on the architectures for the first version of the LUMOS models that we've already deployed. Yes, this is what we'll cover. So the name is called, it's a acronym for large language model series. It's also a spell in Harry Potter that illuminates. It's Greek for light, and it's supposed to be illuminating user behavior. Now names are pretty important because this when I initially wanted to do this 2 years ago, but the name was not right. This is the name that came out with the last thing. No way we worked on a project like this. I can see the date that is 2023. This is when I first this thing, but it was shot down. Then I came up with the right name. The start of this year, and then Palash. So as I said, it's a complete platform right now. It's around 17,000 lines of code, the repository, and with active development, you can see from like almost Jan this year to up till recently. This we all know what this period is when there were no commits, the start of the IPL. We already have through this framework we have already trained models for churn and CA predictions, which have beaten whatever we were previously doing by a good margin. So, in both these models, we had to change less than 10 lines of code to train one of the other models. That's the power of the platform. We've also been able to extract user and supply embeddings, which we want to use in downstream tasks. So, it is currently starting to use it in comps. And these are like very general embeddings that we see recently. And Amit, as he has promised that he'll finally deploy the positive amount prediction model. Because he's already done working with these models. So just about the platform. So there are a few layers. One is obviously the raw data preparation where we spend a lot of time. Most of what we're using is the delta tables and PySpark for creating all these features and doing the feature engineering, getting it into a shape that we can feed it into a model. Then there is training data preparation where again we're using a lot of PySpark, but we're using our own data called Acute for taking the data from a delta table and creating, processing the data, creating batches to feed it into a model. And this also has sharding support, so you can do distributed data parallel using this data loader. And we are considering moving to real data because of some advantages. We're benchmarking it right now. It's not sort of as the performance that we like, but I think by carefully choosing the parameters, we should be able to get it to perform much better than Acute. And then there is the model training, which is again, right now we're doing distributed data parallel with PyTorch, using database jobs for orchestration, ML for log. This also we're planning to move to ray train for better multi-instance parallelism. So with that, that's just the overview of the platform. Now we'll go deep into the architecture for the first few models. And of course, they are fine.
Yeah. Can you explain this term, better multi-instance parallelism, if people to rate it as compared to the PyTorch GDP that we are taking?
So PyTorch GDP also supports multi-instance parallelism through Slurm, but that's very Slurm. So that's sort of a protocol to distribute training across multiple. But it's pretty awkward and needs a lot of code changes. Ray doesn't pretty much out of the box. There's very little code changes that you request. So your per worker function remains the same, and very little code changes that you need to do to move all your Python code to Ray. So basically, the same code works on a single machine, single GPU, and the same code can work on multiple instances, multiple GPU. Very little code changes in that per worker function that you write. Okay. So we'll just quickly go over the LLM architecture. So large language models. So what is the architecture? And this will be a starting point. Obviously, this will not directly apply to what we are trying to do, but we'll first go through this and see what modifications we need to make this adaptable to predicting user behavior. The main components that are there, so this is a pretty simple decoder-only architecture, which most LLMs today are based on. So you start at the bottom with a token sequence of tokens. Let's say you have 10 tokens and you want to predict the next token. These tokens are fed into an embedding. So each token will get like a numeric. So each token is like, you can consider it like a word, but it's slightly smaller than a word. And that word obviously can't be fed into a neural network. So you have an embedding layer. You embed that token to get, let's say, 128 dimensional, 512 dimension vector. So you now have a sequence of these embeddings. You feed it, so you add positional encodings. And why do we need to add positional encodings? Is that will become clear later. Because beyond this point, you have the attention. So you have the main attention block where this sequence goes in. And what happens is a couple of things. So the first thing that happens is there is a communication layer. So all these tokens, they don't know of each other right now. The attention mechanism, the self-attention mechanism, what it does is each token will express itself through first a query, which is you can think of it, what is it that I'm looking for in other tokens? Each token will have a key, which is like what is it that I'm offering to other tokens? And then there's the value which finally gets passed. So each token basically asks, this is what I'm looking for. Every other token will present a key that this is the information that I have. You take a QK dot product, and the value of that dot product will tell you how much value is one token going to give to another token. So each token attends to each other token. And this is how information gets propagated across tokens. So this is the layer that the tokens talk. This is communication between tokens. Then you have a feed-forward layer, which is mostly computation, like a basic feed-forward layer. And this gets repeated n times. So you can think of this like there's a computation, there's a communication, computation, and this is how through each of these blocks, first they communicate with each other to gather context, and then there is some computation that happens. So then finally what you have is very similar to your input. You have a sequence of output. So if you have 10 tokens that you fed, you will have a 10 length output sequence, which will be of, let's say, which will generally be of the same embedded image. And you can use that in various ways. Generally, what you do is you take the last one and you try to predict the next token from that embedding. Right, and that's a classification task, which is, let's say, in your token space, if you have a vocab of 50,000 words, you have to predict the probability of the next word. Right, so these are the four major blocks. So there is the tokenization, which is generally done using something like maybe a byte pair encoding, or there are other different tokenizers people use. But how do you break a text into tokens? How you embed those tokens? How you add position information? So you need to add position information so that when you do this dot product during the attention, through that dot product, the tokens are able to figure out what our relative positions are. Right. So that's how you need. Why do you need the position encoding? And then there's the self-attention where tokens are attending to each other. So these are majorly the components.
So the entire block is self-attention, or only the part is the
So generally this block will go together, but the multi-head attention block is where self-attention.
self-attention. Right. So and n star is basically the number of blocks.
Yeah.
But will that block act parallelly or
No, sequencing.
Sequencing? But for multi-head attention, every head can work parallelly, right?
Right. So we'll not go into multi-head attention, but that's just yeah. So that can happen. So that's within self-attention, you can have parallelism to multi-head attention.
Okay, and why do you? So my question is, if say for example you have multiple layers of self-attention, then why would you keep the feed forward? Like why would you repeat the feed forward thing for every self-attention, and why not to keep it just one self-attention? Eventually you'll just keep on passing the message extracted to the next layer.
Yeah, I'm sure that's a good explanation, but like most things, I think it's probably empirical. You could make the argument that after every phase of communication, you do some processing, so there is some sort of enrichment before the next layer takes on.
Okay.
Like you could make the argument, I can make any other argument also. As most things about this, I think maybe like empirically that works better. So yeah, we've gone over these tokens. First is tokenization. You use something like byte pair encoding to convert tokens. So text is converted into sequence of tokens. Then you have an embedding layer. which is generally learned. So you from these tokens, which is you have like enough into a numerical embedding. Then you have positional encodings, and this is like this is the interesting. So positional encodings are very interesting, and this is one of the popular position encodings, which is the sinusoidal position encoding. So one thing that I always wondered was like, why not just feed the position in as is? Like you have, let's say, a 1024 or a 360 length context window. Just pass in 0 to 359 or 1 to 360. Why do you need to do this sine business, cosine business? Why all this complexity? And the answer lies as to how these positions are expressed. So because you're not really taking, the only way when tokens interact with each other is through a dot product, right? And when you take a dot product, it's generally, if you take a dot product of two vectors, it's generally proportional. Let's say they have equal magnitude, it's generally proportional to the angle between them. Right. So what you want to do is you want to express position in such a way that when you take a dot product, you can get the relative positions and the distance between the positions. So that's why sinusoidal embeddings become a pretty common choice. So these were not, I think, originally they were all learned, all position embeddings were learned, but they figured out that eventually all position embeddings have similar patterns like these sinusoidal embeddings. So at some point, I think it became just conventional to just use them and not have to go through learning them. Right now, obviously, there's even better thing. Everybody's moved to rope embeddings, which is not an additive encoding. So this is position encodings are generally added, but rope is multiplicative and acts during the potential mechanism. So we'll not talk about that. But yeah, that's the rough intuition behind the position encoding. Then that's the important self-attention block where every token attends to each other token and decides what is the value that I'm going to, like, what is the relative value in this to how important is this token to me. And this results in like it's a matrix, right, where each token has a weight that it ascribes every other token. This weight is arrived at by qk. So ith token will have a q, and the jth token will have a k. And the weightage that the ith token will give the jth token will be proportional to qk, right? And then we'll take a softmax to have normalization. And then final output vector will be the values of each token weighted by the attention source. That will be the value of the token. So this is at the high level. And now this is the architecture for LUMOS. So you can see this is significantly more complicated than the LLM architecture. So there's a bunch of stuff that we had to do to apply these same principles. And what you really wanted to do is keeping the self-attention. So the most powerful thing is the self-attention mechanism through which you can have very efficiently address time series patterns. Right. And that's what we want to preserve. But we had to do a lot of changes in and around to use that mechanism. The first thing, obviously, is the tokenization. So it's not really natural for us what the token is. Like in text also it's not obvious, but let's say you start with maybe words and then eventually figure out those words. It's the dictionary is too big. If you use tokens, then it's manageable and still meaningful and stuff like that. So I think it's 1 degree easy to do it with text. But for us, you really have to think about what one token of user activity looks like. So from text, we are going to user activity, where what we want to do is you have a sequence of user activity tokens and you want to predict the next token. You want to know what the user is going to look like. So that's the analogy. But what is a token? For us now, what we've chosen is every token is sort of a summary of a user's activity on a given day. So a day is the time unit on which we've sort of modeled this right now. And on a given day, I can figure out. So let's say I summarize the user's behavior on a given day, and that gives you like this transaction feature. So you can look at the number of total joins, the total deposits, the amount of join withdrawals, wins, event counts, number of raw events produced by the user from events data. And you do a daily aggregation to get sort of a raw vector of what the user did that day. What is also important is not just what the user did, but the context in which the user did that. So it's not enough to know that the user did, let's say, 5 contest joins or deposited some money. It's also important to know what attracted the user to do that. What was the sort of supply there? Right? So you also have every day an aggregate view of the supply. So what is the number of T1 matches? What are the number of India matches? What are the number of IPL matches? Stuff like that. And then you also have some static features for the user which don't vary across time. Like let's say demographics, device info, age at the time of registration, other registration data. So we have all this information. And what we pretty simply do is we embed this info. So let's look at this as three vectors. And what we eventually do is we take these three vectors, we embed them using a simple MLP. We concatenate these three embeddings. We again pass it through an MLP to allow for some interaction to happen to get sort of a final token for the day. So this token now has user information. It has the supply context in which the user did, and also has some information about the user's demographic information. Now, there might be a better way to use the user demographic data because it does not repeat across time, right? So why do you need to add it to every token? So that's something that might change. But right now, this is the model that we're using, is that we finally have the final token, and this is equivalent to the token embedding for the LLM. Right? This final token that we get. So yeah, so after this, we are at the same place as the LLM now, right? So they have a certain way of embedding the token. We created the token, and we have a certain way of embedding the token. Right?
So generally, in case of LLMs, we have like multiple words, multiple tokens, and each token has their embedding.
Correct.
Here only one user, basically one token on
1 day of user activity.
basically here we have only one word only.
Here, so the way that I'm defining a token is one aggregation of a user's day activity.
Yes.
And it's a set of continuous numbers instead of like one token.
So in case of LLMs, we have like a sentence is represented by words and some certain number of words and basically certain number of tokens. But here a user is represented only by one word or one token, and that token is coming from this type of.
No, so
That is just one sentence only.
So one sentence is, let's say, 10 days of user's activity.
Oh.
10 sentence means, let's say, a sentence in this.
The journey is the sentence.
Yeah, the journey is the sentence.
So is there loss of ordinality when we do this? Because obviously in text, B is not greater than A, but here, for example, 10 would be greater than 5, right? So is there like loss of ordinality of that sort happening?
I'm not sure. It might, I mean, how the embedding is formed is sort of, I don't understand. Probably it's not possible to understand.
जो भी normalized है तो आपने देखा है ना?
Yeah, of course, normalization तो किया है, ये सब कुछ किया है, but we just hope that the embedding is learned properly, and if there is loss of ordinality happen, it's happening for very good predictive reasons.
Dhruv, these are just static embeddings, right? Could we probably use a downstream application or?
हाँ, उस पे आ गए. So these are learned. So all these embeddings are learned. So one good outcome of this is because what I could have done is I could have concatenated them before and passed through an embedding. But because I embedded them separately, now I forced the model to learn these separate embeddings. And which is why now you have these three embeddings. You have a user, you have an embedding for what a user does on a day. You have a supply embedding like for the day. You also have user demographic embedding, sort of like which tells you without the transaction data what does the user look like, right? And so, for example, something that you could do with supply embedding is, so I've just plotted this, taken a TSNE of the supply embedding, and you can see that what it is learned is pretty sensible. So blue is no IPL matches, red is one IPL match, and green is double headers. So you can see that in this space, the model has actually learned to distinguish between these. Even double headers have their own separate cluster, right, within this embedding space.
Each dot is a day.
Each dot is a day. That's it. Each dot is a day. So we see that now we're able to do something like supply clustering, and we have some generic day level supply embeddings. Because still not round level, but the day level supply embeddings. Similarly, the static user embeddings you could use for, let's say, new user personalization. Because now you know what is important and you can represent these new users as vectors, or you can also look at other, let's say, every organization apart from Treebear also have this demographic data. So you can have embeddings for them and figure out how would they be on the platform. You can do it for any organization because you learn these embeddings, right? These have nothing to do with Dreamlab. And yeah, so the user static embed, the user daily embedding, we'll see later how we can use them to sort of create some sort of user state embedding, but that will come later.
So
Uh,
this embedding over written with the model itself, transformer.
This was learned by the model.
Would you say
हाँ,
one
मतलब
component will
along with transformer ना? Along with transformer
हाँ, सब jointly learned. Yeah. So this is learned jointly. Everything was learned jointly. Yeah. Now talking about position embedding. So
Dhruv, one thing. This is learned on the auto-regressive task.
this is not auto.
Okay. So
So एक बार हाँ, we will come to that. What is the task
Okay, the
and what
task.
is the sort of predictive paradigm?
okay.
The next thing that we thought would be different was positional embedding. So positional embedding. So in case of LLMs, the sinusoidal position embedding turned out to be the optimum, and so to the point that people don't even bother learning them. We thought that maybe it might not be the best for us, and generally the context window and the dimension of a single token is very large for LLM. So you have a 1 million context window or something. But for us, the context window is pretty short. So let's say last 1 year is 360 data points. So learning the position embedding is not that big a challenge. But if you want to learn a position embedding for like a very high context window, you have to learn a position embedding for each position. And that just blows up the number of learnable parameters. So probably in the case of LLM, it might not be useful to learn the embeddings every time. But for us, we thought that it might need some benefit. And so the learned embeddings tend to outperform for us all the other embeddings that we tried. So what we have not tried yet is like rope, which is like the standard now. But at least in the additive embedding family, learned embeddings generally tend to be best. And we wanted to understand. So just like sinusoidal embeddings came up to be a natural choice for language by training people saw that. We wanted to see whatever we have learned, what does it tell us about the problem itself? Right. So this is sort of very speculative. But what you see here is you see what you've taken. Don't be scared. These are fast Fourier transforms of the embedding dimensions, right? And let's look at the left here. Now, the right side of the axis is high frequency. So in a sinusoidal embedding, what you do is let's say you have 64 dimensional vector. You have low dimensional sine waves and high dimensional sine waves. What low dimensional sine waves, I think I know that. What low dimensional sine waves help you to do is they help you to roughly calculate position. So it's just like city. First you go to the city and then you go to a pin code. So low dimensional sine waves are like very they don't change too much. So they help you locate like positions roughly. And then high frequency sine waves help you precisely locate the point. Right? So sinusoidal embeddings have this property that they have every sort of sine wave. So they have low to high. So you can actually go to any level of granularity that you want to go to. That's why they're used. For us, when we look at our embeddings, most of them learned very low frequency this thing. So the fluctuations are not that much. One like it's not conclusive, but one thing that we can draw from this is probably very high fidelity pinpointing relative questions is not important for this problem. Where you're trying to look at user behavior, maybe it's not that important that when two different days of user behavior interact, whether there's 5 days difference between them or 7 days difference between them. It matters whether it's 100 or 50 days, but it doesn't matter to such a high degree as it does in the case of text. And we also verified this by figuring out if the position encoding. So if you train a model using position encoding to predict the absolute position, sine does pretty good. So using the sine wave, you can actually reconstruct the actual position key, a fifth position key embedding to a very high degree. Using these learned embeddings, you cannot do that. So one inference that you could draw from this is like in our problem, exactly figuring out which 6 दिन पहले क्या हुआ था या 10 दिन पहले क्या हुआ doesn't matter. What matters is more longer term sort of behavior, which seems plausible that it does not matter. जैसे text के case में that this movie was not good, I will dash. Right now, if we remove the word not, right, and put it somewhere else, it might completely change the meaning. But user ke case mein, maybe if he did something 5 days ago or 7 days ago, it mota tells you the same thing. Right? It doesn't change the meaning so drastically. Right? So that's, I mean, again, it's all speculation. But this is sort of what we see.
So what goes data preparation graph?
So the so this is, so you have a position encoding which is, let's say, of 64 dimensions. The first few dimensions will be in sinusoidal angle, there will be low frequency, and as you go towards the right, there will be higher and higher frequency. Right. So these are the first two which are low frequency. This is sine and this is no, this is the lowest star. So this is sine, this is cos. So this is low frequency, then this is high, this is high, this is high. Like this, you will have like 32 columns. Right. So you have a representation for all frequencies so that you can pinpoint positions to whatever degree of accuracy you want to. If you look at these embeddings, here more or less, like it's very noisy because it is learned from random. So I can't expect to be this smooth. But what you can see is there's a tendency more or less to just focus on low frequencies. So that means that just knowing the city is enough. You don't need to know the pin code, sort of, right, for this problem.
In the training data prep that you have done, in that if a user is not active today, does the token itself not get created that day, or you have a vector with mostly zeros in it?
That's a good question. So we are taking all negative samples. So if a user did not do something today, we still say that this is 0, and this was the supply on which he did not do anything. So because that information is important, especially for tasks that we were prioritizing, something like a churn, where inactivity is as important as activity. So yeah, but that's a good thing, and that's something we like thought about a lot when we were starting out. And this is sort of the, like, you'd call it the key difference. Till now, we're still like doing some variations of what, general decoder only this thing do. And this is where we introduce sort of an encoder decoder structure. And it will sort of become apparent why we do this is in self-attention, you have, let's say I'm taking 360 days of a user's history. Self-attention will yield a 360 into 360 matrix. Right, upper triangular matrix, where you have weights where you say that this last, let's say 21st ko whatever user did, that will pay some attention to what he did on, let's say 19th, and so every day will pay attention to every other day, and that's how the self-attention thing will happen. Now, what we really want to do is we want at Dream 11 be really particular about future supply, and everything that the user does will be driven by future supply. How can we figure out can we use the attention mechanism to say that given this is the future supply tomorrow, pay attention to some days. So if there's an IPL day tomorrow, pay attention to what the user did in big T1 events. Right? Can we use the attention mechanism to build something like that? Instead of the past paying attention to the past sequence, can the future pay attention to the past and the right sections of the past to make a good prediction? Right? And that's where sort of cross attention comes. So the original attention is all you need paper actually has an encoder decoder structure because it was meant to be a translation task where you have two sequences. Right? Now it's all about like next token prediction, so it's only decoder. But the original attention paper actually has an encoder decoder structure, which looks very much like. So this is actually closer to the original attention is all you need paper than what the LLM thing is right now.
But Dhruv, we could have added feature supply in that embedding itself. Like for a particular day, we have created embedding. There would have been few more indexes, and we would have added next 5 days, next 7 days, and
Yes.
next month.
But the problem with that is, so if you look at this architecture, this is like this is cut off. But so the way that I'm creating this token, the input token, is what I'm doing is I'm taking user transaction data, I'm taking user demographic data, I'm taking historic supply data, and then concatenating and creating sort of a token. The future tokens only have supply, so I don't want to predict user behavior. I already user static fee. I don't have user transaction information for the future. So for the future, you have a different kind of token which only has supply information. So it's not part of the same sequence because the nature of that sequence is different. It only has supply, encoded supply information and not any. So it's fundamentally different. It's like a different language. That language only has supply. This language has fast user behavior supply. So that's why cross attention sort of way. But there could be n number of architectures where you could probably fit this into sort of a decoder like decoder only structure.
No, मतलब वो encoder भी use कर सकते थे if we concatenate supply जो embedding in future.
So
But
one,
it's a different type of architecture that we
yeah, it's a different type of architecture that you use. So this is like a base architecture. I mean, I'll admit we have not. This has been the same for like last 4 months now. I've not really spent a lot of time working on this architecture because more focus on the engineering part. Naman actually is the person who is most invested in architecture, and he's already made a lot of breakthroughs on the architecture side. But this is just what we started with. This is like the 0th generation of models. But there could be n number of architectures that are this thing. But this is just something that's very, very efficient. So I'll show you later how it compares to other simple architectures and how many parameters those architectures need to do something similar. So yeah, so this is the idea that what you do is you use cross attention. So you have a QKV. Initially QKV, everything was coming from one sequence. Now what you do is you construct the queries from the future sequence, which is the supply. And so that's the question that is getting up. The future supply is asking like, I want to predict this. Which of the past tokens should I pay attention to be able to do this prediction by? So it takes the query for a given date. And then every past day has some K. There is some weightage that is assigned to every past day. And then that's how the that's the value is aggregated and then used for a prediction, right? So instead of being a square matrix, this is like 28. Let's say you want to predict for the next 28 days and you have past 360 days data, then it will be a 28 cross 360 matrix, right? And each row is basically saying this is for, let's say, tomorrow. This is for tomorrow. To make tomorrow's prediction in the past 360 days, which day should I give more attention? And yeah, so the nature of question is like, given the big match next Sunday, what are the previous matches or previous days where I should pay more attention to? So this should ideally learn to pay attention to first, like when I started, my main hypothesis was recency is obviously important. You always pay attention to what happened recently. That has the most important, but also supply is important. So it'll pay attention to some sort of amalgamation of the two.
And
And
it's a single token prediction, no? Next multi-token prediction.
so this is multi-step token prediction, not auto-regressively at once. So it's like predicting the next 5 tokens. Instead of predicting the next token, putting it into the.
But it would depend on also on the winning or losing behavior also. If user get huge loss at the first day itself, then
Yeah. So that's a good distinction. Key why LLMs have auto-regressive. So they have auto-regressive generation. So when I want to generate something, I generate a sample the next token. Then based on that sampling, I sample another token, and there's sort of like there's a propagation of sort of prediction, and there might also be propagation of errors. What I want to do is based on the information today, what is my best guess what will happen tomorrow? What is my best guess what will happen day after tomorrow? Now, when one day passes, I'll again update my beliefs based on the data that I have observed. So I don't need to sample from tomorrow. I can wait one day, get the actuals from tomorrow, and then predict again. Right? I don't need to sample from my tomorrow's prediction to generate day after tomorrow's prediction. I can wait one day and have better predictions for day after. Like, so this is a pretty important distinction of like why we are not doing auto-regressive stuff here. We're not sampling from our predictions. We're actually using these actuals to do multi-time survey. This is something like even I think DeepSeek did this like when they predicted like 5 tokens or 3 tokens in the future. So yeah, so this is the intuition, but it's also interesting to see whether the model has learned this. Now, this is a plot of the attention scores. So the model is supposed to predict what will be a user's a bunch of users. So this is averaged over a bunch of users. The IPL started on 22nd of May this year. Now, what I've asked the model to do is predict what will happen on 22nd. Okay. Now, what is important is what obviously 22nd March. So you can see what are the days that are important? Obviously, recency is important. So you have a lot of weights clustered around here. But you also have these peaks in the past, right? And you can see this peak is actually the IPL final last year. This is the World Cup final. These three peaks are India Bangladesh T20 series. Like, this is the last match. Right. So you actually see that the model has learned to pay attention. So it's using the past supply features. The past supply features pass through the self-attention, communication, computation layers. They make it to the final encoder stage. And then the future and the past can interact to generate this sort of weighted scheme. Where the model is now understanding that if I see this kind of supply, I pay attention to recency always, but I also look for what the user did in similar supply.
Dhruv, this is average across all the layers, this attention?
No, so this is only the final.
Final.
The final decoder.
Okay.
That's
Uh,
good.
But have we observed this attention in every layer? Because I think the initial layer pattern would be different. Probably something which would be totally raw, like actual.
That's why I didn't even look at it. I looked at the initial. No, actually, this model only has one decoder layer.
Then
So then it's not raw.
Then so
Like there are two encoders and one decoder layer. So there's only one.
one attention.
विजन के अंदर भी इनिशियल इमेजेस बहुत रॉ रहती है बाद में जाके उसके
हाँ.
ट्रैक्स मतलब जो भी होते हैं वो थोड़े बॉडी पार्ट्स और अच्छे से
Right. So generally the last layers attention are not that interpretable because they are like the amalgamation of all the attributes.
Because what will happen is that the sense of time itself will become loose in data, right? Because everything is mixed with everything else. It's probably because there's only one decoder layer where the difference is so clear right now.
Then it makes sense.
Right? But that's a good point. If there were multiple decoder layers, then it would have been more like more loose, more diffuse, I think. That's
The recent Anthropic papers have said that after one like a couple of layers, every activation is not a single word now. It's basically a collection of many words, then many concepts essentially. Yeah.
So probably I got lucky that I only one decoder. So but this was good to validate sort of like the hypothesis beyond like looking at just the loss numbers to see that the model is actually learning what you wanted to learn. There's another interesting result is, so we did a evaluation study to figure out what the importance of supply is. And so okay. So what I did was I blocked past supply and future supply one by one. I blocked both of them and saw what it resulted in this thing. So obviously the full model with like both past and future supply works the best. That's obvious. But what is also interesting is when you only use future or only use past, it actually tends to perform worse than passing no information at all. And that's maybe because each only makes sense in the presence of the other. And if that's not there, it's maybe just noise that is a hindrance for the model to learn better. That's one hypothesis. But this is something that's like sort of across experiments I've observed is like that if you just use one, only the future supply or only the past supply and you block the other, it actually tends to worsen performance than to give incremental this thing over using no supply information.
बहुत क्लोज है पर ये
बहुत close है, but that's why we repeated this experiment many times.
पता ना
हाँ, किया.
फेस वैल्यू पे नहीं ले रहा.
Yeah, so now coming to the prediction problem. So till now I've just told most of the results I've shown you is for churn prediction, but the design is to not, so predicting the next token also is somewhere now sort of the analogy is sort of breaking down because we're not really predicting the next full token, we're only interested in predicting, let's say, some attributes like जो user transaction activity वाला जो vector था, I'm only interested in predicting that. And sometimes I'm not even interested in predicting the whole of that. I might be not interested in, let's say, withdrawal or withdrawal amount. I just want to figure out like. And then, so you have like from the decoder output, you can have multiple heads to do multiple predictions. But then the challenge is like, how do you combine these losses where these tasks, the nature of these tasks is different. So some are regression, some are classification. The difficulties are also different. And Krishna has come up with like ways to figure out how to balance these losses in tasks which are both different in nature and different in difficulty. So you don't want the model to be over enthusiastic about something that's very, very difficult. So over time, when you figure out the task is very difficult, there's a lot of uncertainty. You sort of keep the weight down and you invest in somewhere where there's still choose to be had. Right? So that's sort of what uncertainty weighing achieves. So yeah, so this is we're not doing next token prediction. We are sort of doing a mask, not predicting the entire token. We're just predicting a part of the token.
Are we training this whole model end to end, or it's just the last layers we are actually training and initial layers they're freezing?
So there are approaches. So right now we're training it end to end. But let's say, so this is actually what the next thing is user embeddings. The idea behind user embeddings is that if you look at this architecture, especially the encoder. So even if you forget the decoder, which takes future supply and stuff like that, there's a lot of information there, lot of information processing, lot of compute has gone to figure out the final embedded vector, which is very rich. And it's not till the decoder, it's not been polluted with task specific stuff. So it's only decoder when you figure out future supply kya hai, what is the task. But at the end of the encoder, we still have a very rich representation of the user's past transaction history, which could be leveraged to do n number of things. In the extreme case, my vision is that you could use this encoder, condense this encoder, and condense this encoder's output in, let's say, some finite numbers. And every task, most of the tasks in Rivian could be just downstream tasks from this. And they would need very simple models, very light models, and everything can be pushed to the edge. And these embeddings are available in the edge, and then every model is sort of on this. Because you don't need to do all this processing of looking at like last 10 years of 5 years of user data that has already been done. So, but how do you sort of extract this? So one of the problems is obviously you have a complete sequence, right? So you have 360 days ka agar you're looking at history. So you have a 360 into, let's say, 128 D model vector, right? So one of the choices is how do you aggregate, right? So what is the aggregation strategy? Just take a max, there's something called max pooling. You can take just an average. You can take, more interestingly, you can sort of take a recency weighted average, because like recent behavior is more important. What you could also look at is maybe where do you want to do it? Do you want to do it after the final encoder? Do you want to do it initially before the encoder also? Because you have a set of tokens and you have the token embeddings. Can you use the token embeddings to create embedding without the encoder? So you can choose pre-encoder, post-encoder. You can choose the aggregation strategy. You can choose the recency weighing in the aggregation strategy, how much weight you want to give recency. More importantly, you can choose from which model do you want to extract them. Now, if you train a model on a very, very specific task, something like a churn, then the risk is you will learn a representation that's really good churn prediction, but might not generalize. So the idea is you take this from a model which has been trained to predict stuff that would force it to learn different sort of aspects of usability. You want to figure out what type of contests does the user prefer. What is sort of the skill of the user. That's also something like, is it a high skill user? So you want to have a good representation of different orthogonal tasks which you train this model on, and then you extract. And the assumption is that when you do that, your embeddings will generalize well. So for now, what we have is
for different, could be like for different domains you can use multi-headed. How many heads you were using?
Using 4 heads. The multi-head attention will not probably directly let you do multitask. So I think very separate sort of things. Like multi-head attention is a way to achieve
Specialization in different fields.
No, that's probably mixture of experts, something like that. But they're very different things. Multi-head attention generally, even for a single task, you can use multi-head attention. And so even for churn prediction, we're using multi-head attention.
So multi-task training framework is put on top of transformer cohort.
Yeah.
जो heads वाला part है ना, that doesn't help in actually learning individual task itself.
I think not individual tasks, but whenever we get the final embedding at the output of different heads, we get specialization in
On top of that, then that's what Dhruv was discussing.
So then if you look at this architecture, so you can see after the encoder, you have a per task feed forward layer. So every task will have its own specialized feed forward layer, which will take these embeddings after doing the cross attention, and one will do churn prediction, one will do deposit prediction, one will do CA prediction.
Loss combined.
Like So there is, so I think head का दो मतलब होता है, एक prediction head होता है people use, and then there's a head in the attention thing.
Transformer.
हाँ, वो दोनों बहुत अलग है. That's why I think there's a bit of confusion. But they're like different, and we're using both. So we're using multiple prediction heads for multiple tasks, and also multi-headed attention to achieve better
I
parallelization.
was talking about multi-headed.
So this is like one of like some of the earlier like some studies that we've already done in terms of how these choices. So we have sort of a benchmark of 5 different tasks. So one is churn prediction, AUC on churn prediction. One is CA prediction. In CA prediction, I'm not looking at MAPE or R square. They can be very noisy. I'm looking at Spearman rank correlation. So can I rank users based on the CA? There's a public CA. So basically, can I rank users on the fraction that they play public versus special? Net winning AC. So I'm just trying to predict whether somebody is going to be net winner or not. And withdrawal AC, whether somebody is going to withdraw or not. So these are like 5 tasks which are like somewhat orthogonal. And we are training a very simple sort of MLP on top of the embeddings to predict these tasks, and the results are on a holdout. So you can see that generally one is multitask is generally better. Surprisingly, even at that 9.8 is actually a 9.0, but that's still, I think, yeah, that's actually 9.0. But it's still relatively good. I think churn AUC would be probably best. Yeah, still the multitask one has a better churn AUC also. And some you could explain this by saying that the churn model embedding at the embedding stage is still not very specialized because it knows that there's later a very greater deal of specialization for churn prediction. Right? Because it knows that anything that has to do with churn can be learned at the decoder stage. But in the multi-task framework, the model is really forced to learn a very rich representation because it knows that this will be the basis for multiple tasks and has to be a really good representation, right? So this is surprising. I did not expect this, that multitask embeddings will do even better at churn prediction. The single task was obviously churn prediction. Then obviously there's
when you say multitask embeddings are giving better result, तो हम ये बोलना चाहते हैं कि we get the embeddings and then we pass to some normal random forest or execution model.
yes, simple MLP.
Simple MLP, and we are checking it.
Yeah, that is
And we are also comparing the same thing with passing the raw features and getting the results. So first baseline is raw features मैंने डाले जो आपके सब जो initial features थे आपके 32 जो features थे. I get some results AUC. Second, we are passing the embedding of single task and then
So you are saying कि instead of using embeddings, use all the raw data that you
yeah, the raw
पूरा
features.
raw feature सारा use करके, and then you predict, and then see that the embedding
हाँ मतलब
better than better. The power of embedding is actually not it'll probably, if you have the perfect model, there is more information in the raw data for sure. क्योंकि वो information को destroy करके ही condense करके embedding बना है. The value of the embedding is like it's very condensed, it is numerical, and if you think about it, जितना data what you're saying, 360 days of 360 into 32 features versus 128. Right. Then 360 into 32 you will have to collect. Instead of that, if I give you key users state as representation, ये 128 universal vector है. It's very easy to work with that compared to if I say this is 320, this is the representation, and then we'll work. You will so I don't think of a scenario where if you have enough time in compute, you can always do the best with raw data. Embeddings are useful because there's just useful representations which can be very easily, you can train models on top of it, very cheap. So a lot of heavy lifting is done. There is some destruction of information for sure, but it's just convenience.
We should also think in that direction. Yeah, 360 multiplied by 32, it's around 10,000. And here we have 120 100.
हाँ.
10,000, एक तरफ 100.
Right. So वो है. So I did this benchmarking for supply embedding. So if you look at the supply embeddings, right? Supply embedding का chart. So what I tried to do was I tried to predict the DAO using supply embeddings versus the DAO I used only raw data, right? And the supply embeddings were slightly worse off, right? I think उनका R square 89% था, supply का 85% R square. So वो तो हो गए. Raw information will give you better this thing if you are willing to invest like pre-processing training, right? But the beauty of this is like it's only 128 very well behaved numbers, right? So that's the thing. So
Dhruv, is there any significance of the lambda value 0?
yeah, so the lambda weighing recency weighing. So 0 means no weighing. Same sort of treatment for all tokens. So 360 day का अगर history है तो सबको बराबर दिया है. 10 is the most extreme where you're saying that I'm only paying like more weightage to like recency. So you can see recency matters, but it's not consistent across tasks for now. For some reason that ये अपना CA prediction CA does very bad when done very aggressive. So this is like sort of I think, but the thing being that these abilities are a very good starting point for any sort of user prediction task. A very, and you have like right now these are all in a data table like like already using it. And so like these are some of the strategies like
User data development embeddings.
so these are user state elements. User state. This is another sort of listing. You need a transformer, and then this is not fair because I should have compared the transformer with other time series architecture. But that's not. But just a good validation to see if like if I was to throw everything into a fully connected feed forward this thing, even with 4 or maybe I think 5 times the number of parameters, I can't get close to the loss that I've gotten with the transformer. Right. Again, this is not fair. Transformer should be compared to different time series, this thing, but there is value in treating this as a sequence problem. That itself is that actually at least that is validated that there is value here. And philosophy wise, I think one of the core philosophy that we started with was like no feature engineering. Feature engineering is very time consuming. It's a human process. It's you can't backprop through feature engineering, right? You cannot be learned. So there's a lot of listening. It's a lot of compute, right? In our sort of our pipelines, model inference is the minor task. What generally fails is feature engineering. You do all sorts of aggregation on different window functions. There's so much shuffle, right? And massive clusters just to manage all this. Instead of that, I'm just feeding in raw data, and most of the computation is now happening on GPUs, right? And that computation is learned, right? I'm not expecting my biases, right? So that's the most sort of core insight. And what that allows you to do is now that there is no task-specific choices are very few. When I'm doing churn prediction or CA prediction, there was only 10 lines of code difference because most of the difference comes in the feature engineering, which we are not. And then so basically you just choose the loss and you choose the target. And that's the only choice you sort of have to make.
फीचर बनाने में भी कंप्यूटेशन लगता है.
फीचर बनाने में बहुत कंप्यूटेशन लगता है. Generally, most intensive part of the pipeline is feature computation, which we are not sort of doing. And this is not real data. This is like this demonstrative that when you have, and this is obviously when you have sufficient data. Right? This is all conditional on you having. When you don't have too much data, then obviously do feature engineering. Right? You need feature engineering because you don't have enough data. But you have enough data, then don't do feature engineering. Let the data sort of let the model do feature engineering. Vidyas is not there, but he would be very happy.
Dhruv, कितने slides हैं?
Best last one. This is as the future direction that what we are saying. So immediate enhancements comes with already established is like there's a sweet glue activation that works very well. So Naman has come up with this and it's already given us a lot of gain in churn prediction. I think this is neat. And again, the beauty of this is this will be transferable to all tasks. So not because of this activation change, not only do I have a better churn model, I have a better CA model, I have a better dev model. So the swing glue activation was scaling laws are important because we want to figure out are we bottlenecked by the data that we have on the architecture or the number of parameters in the architecture, right? So right now it's most likely the architecture. So what is the right amount of parameters that our model should have to leverage this data? Brute force, train n number of models with different and train it through the whole data set, right? 2 million, 10 million, 15 million, 200 million. That's not sustainable. Generally, what people do is they run short experiments, figure out scaling laws. Data बढ़ाने से कितना gain हो रहा है, model size बढ़ाने से कितना gain हो रहा है. They extrapolate and they figure out to get this level of to extract from this level of data इतना model चाहिए होगा, so that neither becomes the bottleneck. And that's sort of why people fit scaling laws. So Naman is fitting scaling laws for LUMOS, specifically for churn prediction, but I think a lot of things will be transferable to other problems. And yeah, then there's a